Good afternoon. Good afternoon. Right, let's make a start. The most wonderful good Friday afternoon. If you are like me, you are probably tired, you just want to go home and put your feet up and hope that nobody bothers you over the weekend. Am I right or am I right? Thought so. I assume you don't have any other sessions after that one? So it's just basically me who is standing between you and the bed. Okay, let's try to make it as painless as possible, okay? And I hope you forgive me if we don't fill the full 2 hours. But I don't want to make any promises, okay? Good. You all have received email from me today, what we're going to do tomorrow, next week, not tomorrow, what we are going to do next week. So it should be pretty straightforward. So in this first part of this session, I want to expand a little bit on what we have done last week. And I want to clarify a few terms, technical terms, and then show you how we can calculate a confidence interval for continuous data. And that's going to, let me put it this way, this is going to stay with you for quite a long time. And I say that because I'm also teaching on a postgraduate course. And it turns out that some of the students on this postgraduate, on this master's course, find the concept of this confidence interval rather challenging is the right word, I guess. So hopefully by this afternoon, you will be better than the master students. Sounds good, eh? And then in the second part, I will briefly go through the practical that we are going to do next week, Monday, Tuesday, depending on which group you are allocated to. And I can already reveal that experimentally, this is almost an insult to your intelligence, right? It will be, what's the technical term? I think piss easy, right? And you have then to do a little bit of calculations, but again, the calculations are pretty straightforward. So, let's not elaborate on that. What we have done last week was I told you a little bit about this concept of confidence intervals. Confidence interval. And actually, this is a really concept, and I really want you to get that. this confidence interval basically gives you an indication when you take a sample. You take a sample from a much larger population. So that's your population. This is your sample here. And the sample hopefully is representative of the population. And what we do as scientists is from the sample we try to make what is called an inference, an educated guess about the population. You can almost compare that to, for example, if I take a sample of your marks in, let's say, 2 modules, then that is a sample, I can attempt to predict your final degree classification. So in a way, you could argue, why then spend 2 years and a lot of money, or 3 years and a lot of money, if you can already predict what I get at the end? Well, the point is that at the end, you get a degree for what you have learned, not what I've predicted. So it doesn't work that easily. So that's sample, that's population. Population is characterized by parameters. Sample is characterized by statistics. And of course, because it is a sample, we have an uncertainty in it. We can't say, I can't say, your degree will be at the end, you will achieve 67.2568. I can't say that, right? But judging from the sample of your first 3-4 assessments, I can say, I am 95% confident that you will get a 2-1, which is between 60 and 70%. And that is this between. I don't know exactly where it is, but I'm fairly confident that you will get somewhere in this confidence interval. And you probably noticed I gave it a value, a 95%. This is a very common value. I'm 95% confident that you will get this. So this 95%, that is called, or well, 95%. I mean, this is an arbitrary value. I could say I want to be 99% sure. Can I be 100% sure? You can't see him going like that, but he does. Yeah, I can. I can be 100% sure that something will happen, but that doesn't help here, right? So very often we find 95%, or if you want to be even more surer, sometimes you choose a 99% confidence. And this is referred to as the confidence level. So a confidence level of 95% indicates I want to be 95% sure about something. Okay, somebody obviously on the group chat. Shouldn't you be here? Mind you, you can obviously use the group chat for questions. Okay, we've got the confidence level. There's another term which in statistics very often turns up because people don't feel that confident talking about confident levels. It is called a significance level. And very often you find the abbreviation for significance level as alpha. No, don't go for the expensive one. Okay, and if you keep sending in these comments, then I'll turn them off, right? Ben. Yeah. Okay, you should be here. By the way, I know what you look like. And I know that you're not here. This is Rob, you're live on television. Do not swear. People know you. Okay, significance level. The abbreviation for significance level is usually an alpha. And because very often when I set up quizzes or something like that, I can't type an alpha. My keyboard doesn't have the alpha or something, and I can't figure out the keyboard combination. I just simply write it out. It's then simply alpha. Significance level alpha. And for a lot of people, it is a mystery, how do you find a significance level if you've been given a confidence level? Well, the answer is very, very simple. Because confidence level plus alpha always adds up to 1. Or if you like, in percent, it's 100%. So if I say you've got a 95% confidence level, what is significance level? 5%. Or sometimes people fall over, so 95%. So alpha equals 5%, or is the same as 0.05. Yeah, that's this thing. And very easy to convert. Now, last week we discussed the different data types. So we have, for example, nominal, we have ordinal, we have interval, and we have ratio data. We also said we could classify it by discrete data, where you have individual counts, or you might have continuous data, where you don't have individual counts, where you have sort of a sliding scale between different data points. And as an example, last week I gave you this Poisson. Oh, what is the confidence level? The confidence level actually tells us, that's a very good question, thank you, Alex. The confidence level actually tells us how confident we want to be that the population parameter that we are looking at is actually in this particular range that we are defining. Say a little bit about that in a minute. Just let's go back to the Poisson distribution, or Poisson. In this Poisson distribution, we used counts per time or per volume. What? You all right? Okay. Not poison. Poisson. We use counts per volume or per time interval. Counts, raisins per bagel. A typical example. Actually, it was developed by somebody who actually wanted to figure out how many people per year get killed in the Prussian army by being kicked by a horse. And that is what spurred the whole investigation. So I told you the Poisson, the confidence interval is basically we have a count plus minus this magic number 1.96 times the square root of the counts. Now, where does this 1.96 come from? Well, actually, it comes from a slightly different distribution, but this is also something reflective of an alpha of 0.05 or 5%. Where it exactly comes from, you will hear from me when we discuss what is called the normal distribution. But for the time being, let's not worry too much about it. So, for example, and this is a very rough figure or very rough equation. For large numbers, if C is pretty large, it works very, very well. If C is very small, then it doesn't work well. Simply because the conditions of the Poisson distribution are not really met by this, only when the numbers are large. So what would you get, for example, if you tried to have a count of 0? Can you quickly do that in your head? What would you get for 0 with this equation? 0. So you would have 0 plus minus 1.96 square root of 0, and that means 0 plus minus 0. Yeah? And that is where Poisson breaks down, where it doesn't work. Now, I want to show you a better calculator for that, which uses a slightly different equation, the equation you do not need to know. I will give you only data in an exam or in a test or something like that, where I know that you can use the Poisson distribution. So let me check if I find that. Yes. So here's an online calculator. And all you really need to worry about is sample 1. It asks you, I know, he's called Coco, by the way. You will encounter Coco in a later lecture. And you will also encounter some of the cats. Yeah, I know. All we need to worry about is sample 1. Let's not worry about sample 2 or something like that and what it actually tells us. We will deal with that in a different session. So let's say we count 100 colonies on a single plate. And the way you deal with that would be 100 events, 100 colonies on a single plate. So forget this number of days that is just, to confuse. Just replace that with number of plates that you are dealing with. So 100 colonies on one plate. And your confidence interval, in this case, goes from 81.4 to 121.6. Now, what on earth does that mean? It means that from our sample, this sample, 100 colonies on one plate, we are 95% confident that in the long run, if you did this experiment 10 times, 20 times, 100 times, 10,000 times, 185,815 times, you would get a colony count of somewhere between 81 and 122. We round in this case because it's counts. Yeah? We are 95% confident that in this range, in this interval, in this confidence interval, our number of colonies will be placed. Let's say we find 1,000 colonies in 10 plates. What is our confidence interval then? Our confidence interval goes from 94 to 106. And what you see is the confidence interval becomes smaller. Did you notice that? Yeah? So we are now 95% convinced that in the long run, the number of colonies on plates are somewhere between 94 and 106. So the confidence interval becomes smaller if our numbers get larger. Let's do 10,000 colonies on 100 plates. And now our confidence interval is between 98 and 102. It's getting really small, simply because we have counted so many plates that we have a lot of information. So the bigger the numbers, the smaller the confidence, the more information I have, and the more probably accurate and precise, and we come back to these terms, accuracy and precision, the smaller the confidence becomes. Does that make sense to you? And with this online calculator, and I think I've sent you all the link to that, you can play around and use that for future calculations. Okay, so, hang on. I wanted to show you what happens if we put in 0. 0 colonies on 1 plate. This actually gives you a confidence interval between 0 and roughly 4. So even if you have no colonies on your plate, you can say, in the long run, I believe there should be between 0 and 4 colonies on the plate. So basically you can say to, if this is your supervisor or practical supervisor, oh, you didn't get any colonies. Oh, you made a mistake. And you can say, no, I didn't make a mistake, because yes, there might be no colonies on the plate, but in the long run, I would expect somewhere between 0 and 4 colonies. Just record the face of that supervisor, because usually they don't understand Poisson distributions. In the best case, somebody will say, you are totally bonkers. So this is where the Poisson calculation basically breaks down, and this calculation here on this website I would trust more than this, just simply this basic equation that I showed you. Make sense? Brilliant. Okay, now so that was for discrete data with a special definition, counts per volume or per time. Now let's look at continuous data. So continuous data. Again, the same thing. Sample. We calculate a sample mean. And from this sample mean, we try to make a prediction about our population mean. And for the confidence interval, and I abbreviate that as CI, confidence interval, the equation for this confidence interval is sample mean plus minus a critical T factor in this case. And I tell you what it's all about, this critical T factor. Critical T factor times, and here comes an old friend. Sam. Hi, Sam. What does SEM stand for? Loud? You're absolutely right. Standard error of the mean. You're absolutely right, Alex. It's the standard error. Can you remember what that SEM, what the standard error of the mean actually was? It was S. What was S? What the heck was S again? It was the sample standard deviation. Brilliant. Excellent. Sample standard deviation, and in this case, divided by root n. Yep, by S divided by the square root of the sample size n. So we can write T crit oh well, I tried to be good, hey? Critical value times S over square root n x bar plus minus, and this thing also has a name. Everything in life has to have a name, and this is referred to as the margin of error. Or simply abbreviated, very imaginative, MOE. Please don't try to sell it to me as MOD. That's the Ministry of Defense. Somebody did that last year in an exam. I didn't buy it. So MOE simply is a critical T value times the standard error of the mean. And what you get now is the confidence interval now if you look at it from this equation here, would you expect this confidence interval to be symmetric around the sample mean, around x bar? Is it symmetric, or is it sort of somewhere weird? What do I mean by that? Is this difference here the same? Yes, it is. This difference here is the MOE. So you have the margin of error to the left and to the right of the sample mean. And together, this gives you the CI. Okay, make sense? So far, so good. And we know how we can define this MOE. So all we need to do is actually figure out what this critical T value is. And for the time being, just simply treat that as a sort of adjustment factor, because that is what it actually is. It is an adjustment factor, this T critical. It is an adjustment factor for this standard error of the mean. Now, what does T critical actually depend on? T critical depends on two things. That's not ours. Don't worry. T critical depends on two things. It depends on our significance level. And it depends on another factor, and that is related to the sample size. But because that would be too simple for you guys, very often or usually you will not find a reference to sample size when it comes to the critical T factor. It is usually referred to as a degree of freedom, or abbreviated DF. The degree of freedom just simply is how many things do I measure minus 1. Yeah? So if I have a sample size of n equals 10, my degree of freedom is 9. Pretty straightforward. In most cases, it is minus 1. There are some cases where the degree of freedom is different. Could be 2, sometimes even 3. Depends on how many parameters you are actually looking at. But here, where we have only one parameter sample, it is n minus 1. You're still with it? Brilliant. So, where on earth do we find T crit? There are two options that you can find it, where you can find it. One that probably you have been told in A-level. If you've done that in A-level, where would you find the critical value? Loud? I think I heard something. In a table, in the famous T table. Have you all worked with T tables? Yeah? You love them. Let me see if I Oh yes, here it is a wonderful t-table. Remember that? Yeah? Hate it. Now, these t-tables, or this particular t-table, is quite nice because at the bottom it has the confidence level. So very often you will find that we are working with a 95% confidence level. So this is this column here. Yeah, 95% confidence level. And we also know that it depends on the, let's see if that works. No, it doesn't work. Nah. It depends on the degree of freedom, and this is in this column here. Yeah, so your degrees of freedom are given in this column, in the first column. So, the way you deal with that is I wonder why it doesn't work. Oh. So if you want to find, for example, the degree of the t-value for a sample size of 7, yeah, 95% confidence interval, a sample size of 7. How many degrees of freedom sample size of 7? 6. So you would go in the first column, sample size 7 is 6 degrees of freedom. That's between the first white and the bluish bit. You see that, yeah? And then you go over to the 95% confidence interval, and you read off the t-value, the critical t-factor is 2.447. Yeah, can you see that? 2.447 for the 6 degrees of freedom, i.e. sample size of 7, 95% confidence level. Okay, happy with that? The other option that you could use is actually you can use any spreadsheet program, and it has a function. Let me write this function down. In any spreadsheet, it is t.inv.2t your alpha, your significance level, comma, degree of freedom. That's the function that you can put into Excel or Google Sheets. I show you. So we have equals t.inv and it asks for the probability, which is the same as the significance level. So this is 95% confidence level. What's the significance level? 5%. So that would be 0.05, comma, and we've done sample size of 7, degrees of freedom 6. Let's see what we get. We got, in this case here, 2.447. That's pretty much the same value that we read off the table. Yeah? So you've got two options. Now, in an exam or in a test, I do not expect you to remember t-values by heart. I'm fully aware that you don't have access to spreadsheets in an exam. So either I give you a t-table, or I will simply tell you the t-value. So don't stress about it. Make sense? The whole thing? Fantastic. Now, where am I going? Yes, I'm going here. I think I've emailed you the link to practice questions. These are unlimited practice questions. And this is something for you to play with. And here you can do your calculations. So for example, in this case here, there's a calculation where you can try to figure out what is, for example, my margin of error, what is my confidence interval for these data here. So please, please, please practice these things. Okay? Now, the whole thing is entitled Precision and Accuracy. And I believe this is part of the A-level syllabus, isn't it? Precision and accuracy, you have discussed that. Just a very quick reminder. Wrong one. It's when you have too many windows open. Precision is just simply when you want to compare data with themselves. So you measure some data, and all you want to do is you want to look at, do the data make sense in themselves? In social sciences, this is sometimes referred to as internal validity. This is precision. All you want to do is you want to describe the data. That's why precision also sometimes refers to as descriptive statistics. That's descriptive statistics. And for precision, what we do is we treat our data as a population. This is all the data that we possibly could ever have measured. So precision, population. It will tell us what is the spread. So we would use a population variance or population standard deviation and a population mean. Yeah? This is when we want to get precision of the data. This is basically when I collect your marks and say, well, Richard did very, very well. He got 95, 98, and 90. Excellent. Brilliant. Yeah? I do not make any predictions. I just, the data, this is what it is. In contrast, we have the concept of accuracy. And in accuracy, in social sciences, this is also sometimes referred to as external validity. And we are going into the area of inferential statistics. With accuracy, we treat our measurements as a sample. The sample series of measurements, you have done these measurements, and now what you want to do is you say, I don't give a flying flamingo about actually this particular sample because somebody else might have measured it slightly different. And a sample, don't forget, when we take a sample, what do we always have in a sample? Sampling error. I told you, it's like herpes. Soon as you do sampling, you've got a sampling error. Yeah? Sampling error is unavoidable, like herpes. So, because of that sampling error, there is a degree of uncertainty in it, and that is where the confidence interval comes from. With the sample, then you can say, right, I predict to be the true population mean to be somewhere in this confidence interval. So, for example, I have a confidence interval if I measure, for example, some metabolite in the blood. My confidence interval, and we always need to say what confidence interval. Let's say a 95% confidence interval goes from 100 milligram per liter to 120 milligram per milliliter, per liter. Excuse me. This is my confidence interval from which I get from the sample. Every sample always, by default, has a confidence interval, because I can calculate a standard deviation, I have a sample size, and I can find out the critical t-value. So whenever I take a sample, I always, by default, have also a confidence interval. So with this confidence interval, I can say I'm 95% sure that if I did this measurement 10,000, 10 million, 10 trillion times, the true population concentration, the true population mean of the concentration would be somewhere between 100 and 120 milligrams. I can be 95% sure. Now here's a question for you. I have this confidence interval, and I look up the published concentration in a healthy individual to be, so published or known population mean. The known population mean is 150 milligram per liter. So what does that look like? I have my confidence interval, that's the lower bound with 100, and that would be the upper bound with 120 milligrams per milliliter. And I find that my true population mean is somewhere here. First of all, is this true population mean included in the interval? Is it? Yes or yes? No, of course not. Yeah? Trick question. Ooh, there's something weird going on. I predict to be the population mean somewhere in here. That's the red bit. But in fact, it is somewhere else. Could it happen? Is that possible that it happens? What do you think? Sort of, some people go like, it's quite interesting. When I first visited India, I discovered that a lot of people do this head woggle. And I thought, oh my God, I've said something that they totally disagree with. No, it was sort of confirmation. Do we have people from India? Anyone? Yeah? Is that a typical thing, the head woggle? I think it is. So you have to get used to that. And I saw a few head woggles. Can that happen? It can happen. Yes, you are absolutely right. It can happen. How often does it happen? Sorry? 5% of the time it could happen. Why? Because we are only 95% sure, or in other words, if we took 95 samples, we would get, if we got 100 samples, we get 100 confidence intervals, right? Because each sample has a confidence interval. And 95 of these 100 samples would usually contain the true population mean. We don't know what the true population mean is, but it would be contained. But 5 samples might not have the true population mean. For example, we would not be able to say, were we just unlucky that we didn't get the confidence interval and the true population mean matching? Or is something really, really weird going on? Now, if I see something like that, I'm mindful of, it's not exactly what I expected at that point, but it could potentially happen. And we will learn actually later on, when we properly do inferential statistics, we will learn how we can put a value to that, how likely it is that something like that actually happens. Yeah? If we got, however, if we have another, just let me get rid of that. What would be if we had 110 published? It would be pretty much in the middle here. Could this happen? Yeah, of course it could happen, because that is within our prediction. So we predict the true population mean to be somewhere between 100 and 120. We find out that the known population mean is 110. Hey, cool. Nothing exciting. Let's go home. No. But is fine. Life is good. And we don't have to worry about things. Make sense? I suggest we have a 7.5 minute comfort break, and then I'll tell you what we do in the practical. Okay? See you soon. See you at 5 past.
what does the S on the top? What's
That's the
that?
sample standard deviation.
The sample stand. Okay, thank you.
Yeah? And you remember how this is done? Sample standard deviation.
That-
Don't worry, we will revisit
Yeah. I've got
it.
the notes on it. Thank you.
I literally don't understand any of this. Like, I'm really struggling.
Okay. Where is the issue?
I just,
Doesn't make any sense to
just statistics just doesn't work with my head.
you. No, I understand. Just simply totally scratch the issue. This is not statistics. Call it something else.
Okay, well,
Data
this
analysis.
Data analysis doesn't work in my head.
It does. I'm absolutely convinced. Now what I want you to do is, you've got the link to these practice pages. Okay? There are video tutorials on it.
Yeah.
Have a look at these video tutorials and try to figure out exactly how I did it.
Yeah, it's just
Yeah?
it's just the thing is it's like I just sit here and I just get more and more frustrated because I just
No,
don't
no.
understand it.
No, don't get frustrated. If this leads to frustration,
Yeah.
my advice would be stay at home, watch the live stream on my YouTube channel. Yeah, because then you can. So and the video will be still there afterwards. Yeah. So just take it bit by bit. Yeah, and say right. Today I am learning about calculating a population variance.
Yeah.
Look at the video, give it a go with the practice question.
Yeah.
Yeah? Because what I definitely don't want to happen is that you, as soon as you see numbers and your brain processes, oh, this is statistics, I shut down.
Yeah, no, because that's the thing. Because like I'm really trying to like understand it. It's just I think like so I went over like standard deviation the other day, and it literally took me like an entire day to like understand
Okay, but you understand it now.
it. Ish, yeah.
Yeah. So, what
So
we've
it's
done
just like
today.
this. It just goes so quickly.
Okay.
Like, I just find that it goes so fast in here. I'm just like,
Actually, okay, it's a good point because I will do the maths refresher next week. That's
Yeah, I'm gonna
basic
go to
stuff.
that.
You go to that. And then in week 6 again, another one
okay,
where I can include something like that.
okay,
Yeah? But in the meantime, please have a look at the videos
okay.
because I do them for a purpose.
Yeah.
The tutorials. Have you looked at the tutorials?
I've looked at some of them, but I think by that point I was just in a
Just,
point where I was just not.
don't give up.
Yeah.
Don't give up. It will come to you.
Okay.
I had somebody like you last year, and she said, I'm hopeless. As soon as I hear statistics, I can't do it.
Yeah.
I can't do maths, she said.
Yeah.
And by the end of the year, she said, I want more maths because it makes sense and I understand.
Yeah.
And I said to her, what have you been smoking for breakfast? Yeah?
Yeah.
It will come, and I'm happy if you still, after week 4, if you still say, no, can't do it, let's sit down together, let's have a session, and let's see what we can do.
So do you reckon I should go home now and try and watch it?
Yes.
Okay.
No, because we do the practical now. And I tell you what you have to do in the practical.
Right, okay.
Yeah.
So we're not doing any more maths?
No,
Okay.
hardly any. I just tell you what you need to do in the practical.
Okay.
Okay?
Cool.
Don't give up.
Alright. Cheers.
Sorry.
I didn't really get what you meant by this, was it? About internal and external validity.
Internal validity, these are phrases that social scientists use. Yeah? Internal validity means, are the data consistent in itself without comparing it to any external thing? Yeah? So in a way, this is when somebody throws darts at a target and the darts are close together. This means, yes, I get it right. Yeah, the move. That's internal validity. That is precision.
Is that like correlation then?
Not yet. Precision. This is our dartboard. These are the darts. High precision. Here's bullseye. High precision, but not on target. Yeah. Accuracy is they are spot on target. But here, I know what the target is. I have an external reference point. Yeah. Does that make sense? So here, this would be if the darts are like
So
here.
accuracy is getting it onto the target.
Onto the target.
Precision is getting it in one spot.
Exactly. Yeah.
It's just because you said precision leads to population.
So
It doesn't lead-
here, when we deal with precision, we don't compare it to anything outside. So we treat our measurements as a population. That's the whole population. We treat our measurements as the population.
Is that measurement from the sample?
We treat our sample as the population. Yeah. Whereas here, in this case, we try to make a prediction. Where is the target? Yeah. And in order to do so, we need to know where the target is. So we treat the sample as a sample and not as a population. Make sense?
So it's just treating the sample as the population.
And if I have measurements, I have these two options. I can treat it as a population.
Oh, you were talking about that last week, wasn't you?
Yeah. I can treat it as a population, then I use all the population stuff. Or I treat it as a sample. So I treated the measurements as a sample, and then I can make further inference. Yeah. Next.
So I was talking about Poisson distribution.
Yeah.
I came up with a formula. Let's find it. I'm not sure if I should be worrying about this now.
Don't worry about it. That is the official equation for a Poisson distribution, and it depends on the parameter lambda and x. Yeah? We don't need to know at this point what lambda and x is. Don't worry about it. This is when you want to do computational analysis of data and don't have Excel or something like that. Then you would go down that. You would have to integrate that. That's going to be a total and utter mess. Don't worry about it.
When you were covering Poisson,
Yeah.
you said that the larger the sample, the more accurate the results. What would a large sample?
I would consider a large sample anything above, let's say, 50.
Okay.
But this is, yeah.
Okay. I'm with you.
So, and I certainly would not trick you.
Yeah, no, of course.
Yeah. So if you have this link to this online calculator, I would always do that with the online calculator because it's, it doesn't.
Alright, thank you.
So what is the relationship between the formula you showed and the formula in this formula? Is there any relationship?
This is the exact description of a variety of all Poisson distributions that you can think of. Yeah? The equation that I showed you, that is sort of, yeah, it works most of the time, yeah, and it's easy to do. With this, you struggle because, again, you would need to find this lambda, you would need to know what this x is, and eventually you have to integrate it. You don't want to do that. Trust me. Because Poisson is not you can't integrate properly. You have to do all sorts of weird tricks. Okay? Okay, ladies and jelly beans, we are back, right? Now, next week in the practical, it's going to be, as I said, P easy. Because in the practical, you will, the aims of the practical is you have to do a few measurements. You have to get familiar with pipetting. We've used pipettes before, yeah? Everybody? Gilson pipettes? Who has not used these pipettes? Let me show you. Who has not used these pipettes? Some people have not used them. Okay, good. I'll quickly run through how you use them. So you use these pipettes, and then the other learning outcome is that you can do calculation for precision and accuracy with the data that you get, right? So, what does it look like? Next week, you will collect 9 Eppendorf tubes. 9 what? Let me see if I can do that. Eppendorf tubes, or lovingly known as EPIs. They are small plastic tubes Can you see them? Yeah. They are plastic tubes, EPIs. You find them in the lab. They hold about 1.5 milliliters. Good thing is you can close them. What was that? Okay. So you collect 9 of these EPIs. Got them, yeah. So 9 EPIs. And what you do with them, you label them. You have the A tubes, B tubes, and C tubes. 3 times A, 3 times B, 3 times C. You label them, you put them on the balance, on the scales, and determine the weight when they are empty. And ideally, what you would like to do is you have A1, A2, A3, B1, B2, B3, and C1, C2, C3. So you know which one is which. So, and you record the weights empty. Then you use your pipettes. And I can't remember exactly if it is the right order, but to the A tubes, you add 200 microliter each. 200 microliter of water. So you have 3 tubes with 200 microliter in it. To the B tubes, you add 400 microliter, and to the C tubes, you add 1,000 microliter. Yeah? Now, with these pipettes, again, let's see if I can do that. These pipettes, these are these beautiful pipettes. I tell you what, some researchers actually develop a semi-erotic relationship with their pipettes. If you hate your pipette will hate you. And these things cost about, well, because I know the rep, I get a set of 3 pipettes. Yeah, you heard right. Yeah. Because I know the rep, I get a set of 3 pipettes for £1,200. Because they are precision instruments. Most of you have worked with it, so yeah, hurry. Hang on. It is true, it is. So you have blue pipettes, obviously here it is blue, knob on top, and you always have to use a pipette with a tip. Where's my pipette gone? There. So at the moment I don't have a tip on, right? This is, perceive the tip almost like, well, it protects the pipette. So a blue pipette requires a blue tip. Would you use a blue tip with a blue pipette? And the answer is absolutely yes. Where's my pipette? So here now the pipette has the blue tip. Right? And this pipette here, it conveniently is labeled, is a P1000. That it means it goes from 200 microliter to 1,000 microliter. Yeah? And I get always asked, how much is what? Now, it has a bit of a problem focusing. It focuses on my shoes, which is not terribly helpful. So in this case here, you've got the measurement here, and you just about can see it is, what is it? It says 81. For the blue pipette, 81 means you have to multiply it by 10. This means 810 microliter. You see 810? So let's change that. How many microliters is that now? 890, right? How many is that? 550. Yeah, it's not 55 microliter, it's 550. You have to imagine that down here there is a 0. You also have the yellow pipettes. So this is a pipette that goes to 200, it's a P200. Big question, what kind of tip do you use for that? A yellow tip. A good bioscientist always has tips and Eppendorf tubes with them. Make sure that the tip is nicely on. Do me a favor, don't try to force a yellow tip onto a blue pipette. It's not going to work. Make sure that the pipette and the tip are nicely connected, that the tip doesn't fall off. Right? And when you pipette, a pipette has 2 pressure points. The first pressure point, and if you feel that, you can easily feel that. The first pressure point, you reach, you press the pipette down. When you want to load the tip, you press it down, you go into your solution, and you go absolutely straight in. Straight like that. Not like that. Right? Straight like that. You slowly release from the first pressure point and see the liquid going into your tip. And when you want to then empty the tip, you gently go into your tube, go to the first pressure point and then to the second pressure point and empty the tip totally. And the best way to do that is to have it, the liquid going down the wall of the tube. Yeah? So, straight, suck it up into your tube, into your Eppendorf, first pressure point, second pressure point. If you, and gently. If you do that, you will find you become a master pipetteer. If you don't do it, oh boy, are you going to have problems. Is there a specific bin for pipette tips? In this case, no, it's just plastic waste, where you then just simply, most pipettes have a sort of a release mechanism where you just press on it and the pipette falls down. Always make sure that your pipette tip is firmly attached to the pipette. Don't nail it to the pipette, right? Because that will break the pipette, but just do it gently. But make sure it is firmly attached. Okay? Happy with that? Can you do that? Yeah. So, you've pipetted your water in your tubes. And what you do then is you measure them, you weight them again. Calculate the weight with the water in it. So you have weight without water, weight with water, and you just simply do the difference. So you calculate weight per tube, weight with water minus weight without water, and you get the weight of the water that you put in, right? Gives you weight of water. So what would you expect for the how much do you think this will weigh? 1,000 microliter, how many milliliters is that? Micro into milli? 1,000 microliter is exactly, you are totally right, 1.0 milliliter. Yeah? 1,000 microliter, 1 milliliter. What is the weight of 1 milliliter of water? It is identical to 1.0 gram. So you would expect that when you calculate this difference, you will find that your 1,000 microliter weighs 1 gram. 200 microliters gives you 0.2 grams. 400 gives you 0.4 grams. Or you can also say this would give you 200 milligrams. It's the same thing. Yeah? 200 microliter gives you 200 milligrams. So what you then get is you get, let's do just the A tubes. You get, let's say, 210 milligram for your A1. For A2 you get 200, and for A3 you get 190 milligram sample or measurements. These are your data. You've got 3 data points. So what you can do is, if you want to calculate the precision of your measurements, you treat these data as the population. So for the precision, and basically, experimentally, this is all you need to do. You take your 9 tubes, weigh them, add water, weigh them again. That's it. I think even my dog would be able to do that. How he's going to fill the tubes might be a different story, but I'm sure he can do that. Now, if we are looking at the precision, we are just looking at how the data compare to themselves. So I can, for the precision, I can calculate the population mean. Can somebody quickly calculate the mean for these data? Sorry? It's 200. 200 milligram is the population mean. 210 plus 190 plus 200 gives 600 divided by 3 gives 200. That's the mean. Yeah, that's the population mean. How do I present these data? No. Rewind. Now, can we calculate the variance of the data, the population variance? So what we need to do is we calculate 210 minus 200 squared plus 200 minus 200 squared plus 190 minus 200 squared divided by the number of observations that I have. How many have I got? It's 3. That would give me my population variance equals 10 squared plus 0 squared plus 10 squared divided by 3 equals 200 divided by 3 milligram squared. Yeah, that's my unit. Make sense? And I can calculate the standard deviation, population standard deviation, and that would be just simply the square root of 200 over 3 milligrams squared, and that is the square root of 200 over 3 milligram. And we've got the same unit, milligram, back from this calculation. So that gives me my standard, my population standard deviation. Yeah, make sense? Happy with that? How do I present the data for the precision? I plot them. So here would be my data for 200, 400, and here would be probably 1,000. It has to have a label. So here is the microliter of water that I add. The rule is, on the x-axis, you plot what is called the independent variable. The independent variable means this is the thing that you basically choose. 200, 400, 1,000. Yeah? This is what you choose. On the y-axis, you plot the dependent variable. This is what you measure depending on your x-axis. So, in this case, for 200 microliter, you get, do you have it, milligrams? For 200 microliter, you get roughly 200 milligrams. And what you can do is, if we've got only 3 data points, it is custom to show these 3 data points. So we have a slightly below, right, and slightly above. So 3 data points, and you would indicate them with these little X's. Yeah? So that's absolutely fine. If you have more than 3 data points, you end up with lots and lots of X's, and therefore people don't like that. So what you do, if you've got more than 3 data points, you represent that with an X, and this one here then is the mean of your observations. That's the population mean for this observation. And you then add an error bar. And this error bar is symmetric around the mean, and it goes usually 1 standard deviation above and 1 standard deviation below. So if your standard deviation is 200 divided by 3, that is 66.7. Is that right? Have I done that right? 66.7? So the 66.7 would be above and below. That would be your error bar. And that is the correct way of doing it. Yeah? That is the precision in this case. Does that make sense? That is what I want you to do for 200, for 400, and for 1,000. Yeah? Now, we also can treat, and remember, for the precision, we treated everything as the population. I also want you to do the accuracy for that. And we use, again, the same values, 190 milligram, 200 milligram, 210 milligram. And now we want to do the accuracy. And for the accuracy, again, we calculate, in this case, population or sample. What do we use? Accuracy is loud? It's the sample. So accuracy is sample. So we treat that as a sample, and therefore we calculate x bar. That's our sample mean. What's that in this case? Still 200 milligram. We now calculate our sample variance. 190 minus 200 squared plus 200 minus 200 squared plus 210 minus 200 squared divided by what? Loud? N minus 1, exactly. Because we have a sample, we do n minus 1. Don't forget that. Yeah? So we have 100 plus 0 plus 100 divided by 2 equals 200 divided by 2 gives us 100. So that's our sample variance, and now we can also calculate the standard deviation. Standard deviation is simply square root of 100 equals 10. Yeah? That's our standard deviation. Well, actually, we are not terribly interested in a standard deviation in case of the sample, because for a sample, we now can go away and predict a confidence interval. And I want you to do that as well. So, confidence interval for this sample. And we know how to do that. It is x bar plus minus the critical t factor times our standard deviation divided by square root of the sample size, and this, in this case, we have 3 divided by square root of 3. This gives us a confidence interval. We can quickly do that. T crit, and we go for a 95% confidence. Let's get back the table. So we've got a 95% confidence. How many degrees of freedom do we have? 2. Can you read off the critical t value for 2 degrees of freedom, 95 confidence? 4.303. Absolutely right. So we have 4.303 times 10 over square root 3. Bless you. Our x bar was 200 plus minus. Let's see if I can do that in my head. 4.303 times 10 over square root 3. Actually, there's a little nifty trick if you want to impress people. If you do 4.303 divided by square root 3, it gives you roughly 2.5. That will do for us. 200 plus minus 2.5 times the standard deviation. So it gives us 200 plus minus 2.5 times 10 equals 200 plus minus 25. Yeah? And what I want you to do then, plot the accuracy. $200, 400,000 microliter, here the milligrams, 200, 400,000. And the proper way of doing that with the accuracy is you indicate with an X the sample mean here. Let's write this properly. And you have error bars. And in this case, good scientific practice is to indicate one MOE, or just the MOE above and MOE below. So in this case, it would be 25 and 25. So what you see here actually is this bit here. This is our confidence interval. But there are other practices. So people still sometimes show error bars as the sample standard deviation or the standard error of the mean, especially when your data are pretty shite. If you use the standard error of the mean, S over square root 3, your error bars will be fairly small. It looks really good. Oh, look, the error bars are small. There are not big errors in it. The guy did really good experiment, you know. No, didn't do any good experiments. They just sold it well. The right thing is, in my opinion, is to use the confidence interval as the error bar, but you also then need to say in the description, in the legend of the figure, error bars indicate 95% confidence interval. So I eventually want you to do that. So you have to do two plots, precision and the accuracy in the practical. You don't have to do a write-up. All you need to do is do these plots, show your data, your measurement, and the calculations. Please always show your calculations. Show that to the demonstrators or me, and you are done. Shouldn't take you more than an hour. How cool is that? Any questions? Practical is clear what you're doing.